We will start with a very brief introduction today. And since we are quite a diverse group, so we have people who haven't had any experience with RL, we have people who work with reinforcement learning. So we've tried to balance this a little bit. So we'll have some formalism, some brief introduction, then we'll go through some basic models, and then we'll go deep into some of them on the future lectures. So yeah, let's consider the reinforcement learning motivation to reinforcement learning on this simple example, which is quite relevant real life example from a robotics perspective. So imagine that you have a task, which is to pick up objects from a box, and you have a robotic hand to do that. And basically what you have is the robotic hand, which has some manipulator, some gripper to pick up the objects, and you have the camera, which gives you the information about the system. So that's basically your eyes and your input. So the task in this case would be basically to, given the input that you get from the camera, so literally RGB image, you need to design some kind of an algorithm. You see my mouse here? Oh, I see in the gap. Basically, you need to come up with an algorithm, and that will, based on this input, give you, for example, the coordinates in 3D space where you want to put the hand of your robot to pick up an object. And traditionally, there were quite a few approaches to do that. So the first, let's say, more standard approach is to understand the problem and to solve it. So by understanding, we mean that we try to create some kind of a model for this problem, and then we try to come up with a usually deterministic algorithm that would consider all the possibilities for the problem, like objects with different shape, different properties, and then solve the problems for them. And there is an inherent problem with that. Basically, the problem is that writing the exact algorithm for every possible situation is usually not possible, because during the exploration of the task, when you're going to use the robot to pick up the objects, you will definitely find some situations where your algorithm doesn't work. So something surprising, for example, if the object has some weird unobservable properties, for example, the mass distribution, which is off, or if the object is soft or behaving in a very unexpected manner. And the more or less classic recent year approach is basically to use machine learning for that. So you reformulate your task as a machine learning problem and solve that. And in a very simple terms, if we formulate this task as a supervised learning problem, this would be the following. So we would collect a lot of data, which would consist of tuples, the input image and the ground truth action. So the action that you, for example, as a human, labeled as the action that you should take in this situation. And given the set of these tuples, you would run a supervised learning algorithm that would, based on the new image, tell you the coordinates where you should put your gripper to pick up an object. And this approach will actually have a lot of problems if you try to apply it to this particular task. For example, again, it's very hard to adapt. Also, you need to collect a lot of samples. And what's more problematic, you need to have a ground truth data. And with the ground truth data, first of all, it's not always easy to understand what's the ground truth. For example, if you're solving a chess problem, there might be no like exact ground truth data. What's the best next move? And in context of more like real world tasks, for example, the control problems, there is also very hard to come up with the ground truth data. For example, if the data that you want to get out of your algorithm is, for example, the forces and the torques that your robot should put in order to reach some point or in order to do some task. Because we don't think in those terms, and we cannot really come up with the ground truth numbers of the forces that robot should exert. And so here where reinforcement learning in general comes. So first, it can be formulated as learning from experience. So instead of providing the ground truth data to the reinforcement learning agent, we let it itself collect the data and try to infer from its experience what's the best action to take in that or another situation. So on let's say a very high level, and from the practical point of view, this would be a lot of robotic hands trying to pick up objects, obviously failing, and then trying to take in that experience, sometimes hitting the correct actions and combining all that in order to improve their behavior and learn from their own experience. So in a very simple scheme, here would be, let's say, a number of robots collecting the data, or a number of other reinforcement learning agents, for example, the AI playing the game. And it would be collecting the data. And in this case, the data would be slightly different from the one that we had in a supervised learning problem. So instead of tuples, input and ground truth output, since we don't really have the ground truth output, we would instead have a combined pair of input and output, doesn't matter correct or incorrect. And instead of trying to come up with the correct action, we would just try some actions defined by initial policy, which could be random, for example, and we just label these pairs as a successful action or failure action. And already here you can see that it's actually much easier to basically try different random maybe actions and label them as successful action or unsuccessful action, or success or failure, rather than trying to solve this problem by trying to figure out only successful actions. So the data collection in this case would be much easier than in supervised learning problem. Basically all this data you would provide it to the reinforcement learning algorithm, which would then take that all in and provide you with some kind of policy. So basically the behavior that's given the input, it would produce some output, some action. And we can actually use that policy to close the loop and to actually use this to collect new sets of data. And now we'll have a improved policy, so probably we'll be hitting successful actions more often, and so on. By iterating over the loop many times, we will hopefully converge to a policy that will always give us successful actions. So there are some different definitions for reinforcement learning that you can find, and but probably the most general one is that reinforcement learning is an approach to learn decision making and control as a type of decision making from experience. So here we don't really talk about how we do it. We don't talk about the rewards or anything else. We just say in general that we learn decision making from experience, and that's something that relates reinforcement learning a lot more to real life tasks than other types of machine learning, such as supervised learning or unsupervised learning, because as humans we often do the same. And although when you're basically learning about neural networks, you often hear that neural networks are inspired by human's brain, and that's essentially the same thing. Although it's quite different. Here, reinforcement learning is actually resembling quite a lot how humans learn, because when we are born, we have very poor policies for decision making, and we constantly do mistakes. And although we have some supervision, for example, when our parents tell us not to do something or showing us how to do things, actually most of our knowledge, most of our decision-making capabilities comes from trial and error approach, so from our own experience. So yeah, and you'll see that actually a lot of this is reflected in the reinforcement learning methods, where basically you can see a lot of parallels with how humans learn. So let's again like oppose a little bit reinforcement learning and supervised learning. So maybe to put it a bit better in the perspective how different they are. So basically, when you're talking about standard or supervised machine learning, in this case, you're usually given data sets of tuples of x and y's, whereas x is input and y is output. And let's say in the neural network, you're trying to predict y from x. So essentially what you do is you're trying to, you know that there is some function which maps x's into y's, and you're trying to approximate that function. And this, like generally most of, or all of the supervised machine learning algorithms, they implicitly assume some things about the data. First, that this independently and identically distributed. So that means that all the samples or all the x's are independent of each other, and also that they come from the same distribution. And that's in principle true for most data sets that are used in machine learning, in the supervised machine learning, but it's not true in many real world tasks, for example, because in many cases, if you're interacting with something, your actions always has consequences. So if you try to actually do something, the output will always influence the data that you will be seeing in the future. So it's quite different. And again, for supervised machine learning, it's true that it assumes that we have the ground truth data during training, and that's again not always true in many real life complicated tasks. Of course, in unsupervised machine learning, we don't have that assumption, so we also don't know the ground truth. But then we don't have any guidance from the real world. And in unsupervised learning, we have the internal guidance of how models should arrange the data. But in reinforcement learning, we actually do have some guidance, but we avoid requiring having ground truth, which is very nice. So in short, in reinforcement learning, the data is not independently and identically distributed, because as we said before, whatever you do, it influences what you will be seeing in the future. And the ground truth is not known. And in general, we do have some guidance, but in the form whether we succeeded or whether we failed. And although just succeeding in failure is just very little guidance, basically true or false, in reality, we'll be mostly talking about the rewards. So, and this is something that's much easier to get than the ground truth data, especially when the ground truth data does not exist or virtually is impossible to attain. The reward is something that's much easier to engineer and much easier to get in general. So basically, I'm pretty sure most of you know some good application areas for reinforcement learning, because they became pretty famous in recent years, and probably the one that everyone has heard about is games, especially whenever it comes from DeepMind group, which was AlphaGo, solving basically the Go game, or AlphaZero that solves chess and is rated 1,000 more ELO points than Magnus Carlsen. So basically the games is an important venue for reinforcement learning to actually showcase its capabilities. And but it's very important to understand that it's not just the games in the most common sense of this word that reinforcement learning can solve. Because if you look at the game theory, for example, you will see that the actual mathematical formalism in game theory is very much generalizable, not only to the games, like the games with rules, and quite many situations. For example, stock markets can be described in terms of game theory, because there are obviously rules, there are actions of the agents, and there are obviously some rewards. So although this might look quite funny and not really applicable, a lot of reinforcement learning can be applied that's used to solve problem in games, can be actually used to solve very serious stuff. So another application that's very close to us as a robotics labs is robotics. Because mostly if you're talking about some robotic tasks, it's a robot having to interact with the environment. And when the robot interacts with the environment, it performs some actions, and it obviously has some consequences. And ultimately, we want these consequences to be the task performed correctly. And there are plenty of applications where reinforcement learning has been used to pick up an object from a pile of different objects, or perform some manipulations with the tools, again, to successfully complete a task. And finally, another big topic that you all heard of is self-driving cars, and in general, like any autonomous navigation, where basically the inputs are taken as in the form of sensor data and, for example, RGBD cameras, and the output should be the action, for example, how much you should steer and how much gas you should put, or maybe you should brake. And the same is for other control applications, not only control in terms of, let's say, robotic applications where you have to control some mechanism, but more like a regulation if you want to regulate a network or if you want to regulate the traffic in some area. That's also something where you have actions, where you regulate something, you have consequences, you can formulate the rewards. Therefore, you can quite easily apply a reinforcement learning approach to the problem. So here we'll start with basically some important definitions and some mathematical formalism that's very important for this course, and not just for the course in general, but for any reinforcement learning activities, because it's quite simple in general. It's quite easy to understand, but it's important for everyone to talk in the same language here, because it's a lot of models can be visually similar, but have some small differences that are very important to understand. So we'll go with some simple definitions. Yeah, and if you have some questions, by the way, just feel free to interrupt or write in the chat. Otherwise, we'll, after this small section, we'll have an opportunity to discuss it in the breakout rooms and then raise some questions if something is not clear. So first, let's fix some simple terminology. So imagine that we have an input, and a very common type of input is the data from RGB camera. So let's say we have an image, and that's the input that we have. And here we will call this inputs O, which stands for observation. And usually it has a subscript T, which indicates that we got this observation at a time frame T. And for now, we can assume that we are talking about a discrete time. So we have the discrete time points, and at each time point, we have an observation and we do something, and then at the next time point, we get another observation. And later on, we'll discuss about continuous time. So we have an observation, and what do we want to do? We want to come up with an action based on this observation. And an action could be, again, a continuous action or discrete action as a selection of certain possibilities. So based on the observation O at time t, we would have an action A at time t. And in this case, it would be, for example, running away from the tiger, or approaching it, or doing something else. And what's actually lies in the heart of any reinforcement learning algorithm is the transformation. How do we get from observation to the action? And this transformation will be called policy, and it will be usually denoted with P. And P essentially gives an action given the observation. And we will be writing P with a subscript of theta, indicating that there are some parameters theta. And in this case, for example, we represent the policy as some kind of deep evolutional neural network. And theta would be the parameters of this network. And after we got the action from the observation, we usually execute this action, and this brings the system to a new state where it will provide a new observation at time t+1. So here I mentioned the state, and the state is something that's quite different from the observation. And so let's say in the situation where we have a cheetah chasing a gazelle, the observation could be, for example, the image or a video, or usually it's a single time point, it's just an image or some other sensor data. But the state would be, for example, the coordinates of the cheetah and the gazelle and their velocities. And we can say that although the state is unknown generally, what we can get is the observation. And one state could of course give phrase to different observation. Yeah, Farzaneh has a question.
Yeah. Hey, I have a question. I didn't get the role of this deep neural network in this setting that you mentioned.
Yeah, so basically, generally we, like in any machine learning algorithm, we have the input and we have the output, right? So the reinforcement learning algorithm gets the input in form of observation, and we want it to output the action, so something that it wants to do. And it does this through some kind of a policy. And policy is basically a function that, given the observation, gives us an action. And in this case, we just represented it as a neural network because quite often the policy is actually a neural network.
Yeah, thank you.
So far there is no special meaning, but it's just nice to represent it.
Thanks.
Yeah, so coming back to states and observations, the problem in general is that states are hidden, so we don't really often know what the state is. And the observation is something that we can easily get from the system. So for example, images or sensor data or something else. And in some cases, states could be as well fully observable. For example, if it's a game or a game of chess, the state is essentially the state of the board. And you can easily use in your algorithm the state itself without using the observation, which would be the image of the board, for example. So as we said, this pi that gives us A given the O is the policy. And sometimes when the states are fully observed, like as I said, as in the games, for example, we exactly know the position of all the pieces on the board. In these cases, policy can go straight from the states. So basically, it will be denoted as pi given A given C. So it's given that we have different time points, it's sometimes easier to represent this in the graphical model. So if we start from a state S1, it usually gives some observation O1, an image, for example. And then using our policy, reinforcement learning algorithm or learning agent provides us with an action. And then when we apply this action, the system goes from state 1 to state 2. And then we repeat this process going forward. And here, basically, since the system has some kind of distribution of possible states, so it could be discrete states or it could be continuous distribution of states, we will always have some kind of transition probability. So what is the probability that we end up in the state st plus 1 given the current state and the current action. And if we repeat this going forward, so that we will be going through certain states, seeing observations, given actions, and executing actions, going to the next state, and so on. And here you can see that actually there are some invariant things in this scheme. And one of these invariant things is that the transition probability from state to the next state is actually the same every state, because it could be, for example, a matrix or a tensor that given the state and an action, you transfer into another state with a certain probability. So, and given this scheme, we have certain independency. So you can see that st plus 1 state doesn't depend on st minus 1. So it only depends on the previous state, because we have certain transition metrics. Given the state, given an action, we end up in another state. And that's a very important property that's called Markov property. And we'll be talking about it very soon. So let's consider maybe a little bit different example. More realistic is when you get image from the onboard camera of an autonomously driven car. So you get the observation, you have some policy that tells you based on the observation which action to take, where to steer, for example. So how do we decide which action is better or worse? Because we need to give some input to reinforcement learning model. And the way it's done is through the reward functions. So typically the reward function is defined on the state and on the action, and it provides some scalar function in the form of reward. So higher value is higher reward and lower value is lower reward. And basically this is the function that tells us which combination of states and actions are better. So basically in which state, which action is the best one. And of course, this could be like, you can imagine that if, for example, if in some state you keep doing some actions that lead, for example, to the fact that your car stays on the road and drives fast, you will be getting higher reward. And if you crash, for example, or get off the road, you get lower reward for those sequence of states and actions. And if you look at what we have so far, is that we have states, we have actions, we have some rewards, and we have transition probability. And all these components together, they define a Markov decision process. And if you don't know what that is, we will briefly cover it in the following slides. So first, we start with the most simple thing, which is the Markov chain. And Markov chain is basically defined as a set of two things, S and T. S is a set of states, and basically it's just a combination of all the possible states that the system can encounter. And it can be discrete, like in the games, like in chess, for example, and continuous, like for example, if you have some like continuous signal from a sensor, then you get continuous state space. And D is a transition operator. And it basically describes the transitions between the states. So here, for example, if we have state at the time t, you have the probability or certain probability of going from state st to state st plus 1. So imagine that we have for now the discrete set of states, and let mu ti be in the probability that at time t we end up in the state that has the number I. And basically you get a vector of probabilities, because for each I, for each attainable state, you get a vector where you, at time t, you get a distribution of possible states at this time. And then if you set matrix T with the T, II, IY, IJ element being the probability of going from the state J at time T to state I in time T plus 1, then you basically define a matrix which represents a transition matrix between these two vectors of probabilities at time T and time T plus 1. So that means that if you have certain distribution of the possibilities of states at time t, then you have this transition matrix which you multiply by this vector, and you get a new distribution at time t plus 1. And again, here we can see that the transition matrix is just one single matrix. It doesn't depend on time, which means that basically at each time step, the distribution of the state probabilities at this time step is only dependent on the distribution at the previous time step, and we always multiply by the same transition matrix T. And if you look at this, you will wonder, like, okay, we are multiplying by T all the time, and then we are going through some states. Do we ever end up in the situation where we don't change the state anymore, or the distribution of the states? And there is such property of a Markov chain which is called a stationary distribution, and that indeed is state or distribution of the state probabilities mu, such that satisfies this equation, so which mu equals T multiplied by mu. And this of course, this stationary distribution doesn't exist for any transition operator. And to this stationary state distribution to exist, this transition operator should satisfy a couple of conditions. And one is ergodicity, which means that we can eventually go to any state with non-zero probability. And it has to be aperiodic, obviously, because if it's periodic, then we will be iterating through a number of states, and we don't get the distribution stationary. So now we'll go to Markov decision process. So in general, Markov chain is quite an old term. It's like over maybe 150 years old, while Markov decision process is relatively new. So it's been developed in the around 50s, last century. So here we augment the Markov chain with two other things. So one is the actions, and R, which would be the rewards. So again, we have the state space. We have a system that can attain different states. And we have an action space. So basically, by applying some action, we can go from one state to another. So now we don't have a certain transition operator that goes through one state to another, but we also depend on the action that we take. So that means that transition operator now will depend both on the state and an action. And it is now not a matrix, but rather a tensor. And similar to before, if we set, for example, mu t, tj as a probability that at time t we are in the state j, this would be the distribution of the probability of the state probabilities at time t. And we let state t k as a probability action k at time t. Then we can define a tensor element, the ijk, which defines the probability that if we are at a time t in a state j, and we take an action k at time t, then on the next time step, t+1, we end up in the state I. And again, here we have, in addition to the state chain, we also have the actions. And now the transition probability depends not only on the state, but also on the action that we take at time t. And on top of that, we get a reward. The reward function is basically defined on every pair SA. So it's defined on the product of the state space and action space, and it gives you a scalar value, which would be the reward. So now we've been talking about the states mostly, and we started from the fact that we don't always observe the states. Sometimes we observe just the observations. And for this, there is also more mathematical abstract called the partially observed Markov decision process. And now we augment Markov decision process with the observation space and the emission operator. So now again, we have states, we have actions that take us from states to states. And now we also have the observation space. So now each state corresponds to some kind of observation, or it could be a distribution of different observations, because different observations of the same state are possible. And then we have actions. And then again, we have a transition operator that takes us from S to another state, considering an action. And here we also get the emission probability, which defines of the probability distribution of different observations given a state. So, for example, if we have a state of a cube being in the center of the coordinates, we can still have a number of observations from different views of the camera. And some observations could be occluded with some other objects or something else. So emission probability defines on the probability of getting certain observation given the certain state. And the reward function is the same. So now we can formulate the actual goal of the reinforcement learning based on this, these definitions. So again, the goal of reinforcement learning is to get a policy. So to get something that, given the state, tells us what action we should perform. And to get the policy, it's not enough to just define like a structure of like what should it be? Should it be like a decision tree, or should it be a neural network? The most important thing is that we have certain parameters that we want to optimize. So we want to find the optimal parameters that give us the best policy. And having this policy, we will feed some states into the policy. We'll get some actions. And then we will be applying actions to the states. And since we're usually working with some real world systems, we will observe some kind of probability distribution, given that we have a state, we have an action, and we'll be getting some different next states as time. And by doing that, so feeding states into the policy, getting action from it, applying this action, getting a new state as prime, we will again be closing the loop by feeding the new state into the system and iterating over and over. And somewhere in this loop, we'll be having learning, and we'll talk about that later. So here, let's define the notion of trajectory. So basically, so far we'll be talking about having state and an action, but in reality, we always perform a series of actions, right? And any real, for example, robotic manipulation task will be involving a lot of stages. When we want to reach with the robotic hand somewhere, there is a lot of different small actions, like moving somewhere a little bit, turning something a little bit. And there are a lot of joints and a lot of different steps. So in general, we'll be talking about some trajectories. And by trajectory, we mean a series of state, action, state, next action, and so on within some time period t. And it's important to have this trajectory in terms of, it's important to have some horizon of events, because we almost never want to have to optimize just the next move, because we could be making some mistakes, for example, some small mistakes, and then at some point the mistakes will accumulate and then we will fall off the cliff, for example. And, so we always want to have a certain time horizon in mind and work with that. So here then, having the trajectory, let's define the probability that we have, that we attain this trajectory in the t steps. And this would be, by a simple probability chain rule, will be some net probability of having the state, having the first state, PS1, and then it will be actually the sequence of actions. So for example, action 1, we will get with the by the policy from S1, we'll get action 1, and then we'll get we'll have to multiply it by the probability of getting S2, given that S1 and action 1, and so on. And we continue this T steps, and we get this simple formula for the probability of getting this trajectory. So just simple chain rule, we just multiply the probabilities. I think we'll be mostly using tau as a notion, as a denoting the trajectory. And the goal of reinforcement learning is basically to find the best parameters of the policy, theta, that maximizes the following equation. And this expression is basically what lies at core of basically every reinforcement learning algorithm, is that we look at some, as I said, like some time horizon of length t, and then we, for each of the trajectories, which can be, for example, distributed according to this probability, for each of these trajectories, we look at the sum of the rewards at each time step. And we have here the sum because it's quite logical, because we want to give every time step equal reward, and then the sum is a very common function in the stochastic processes when you're talking about market decision process. So basically, we want to increase the expected reward from the trajectory within some certain time frame t. And the goal of reinforcement learning algorithm would be to optimize this expectancy, so to get the maximum by trying to optimize theta parameters, to get the best policy that will give us the best expected total reward, given the distribution of different trajectories. Here there is a very important transformation, because here we can look at, basically we have a multiplication of these terms, and each of these terms can be considered as basically as a step of a Markov chain, where the Markov chain doesn't include just the states, but it includes pairs of state and action. So in this case, we can imagine that we have state 1, state 2, state 3, and then the policy tells us to get the next state, to get an action given the state, and then given the state and an action, we transit into the next state. So that's what we had so far. This is a typical Markov decision process. But instead we group states and actions, because here we, if we look at each trajectory, it has pairs of states and actions consequently, and then the probability of having this this trajectory can be expressed as the multiplication of these terms, which each one of them can be defined as like one part, one item of the Markov chain. So basically, then the transitions between, for example, ST80 from one state of this artificial Markov chain, the next step would be according to this equation. So the probability of having ST plus 1, AT plus 1, given that we had ST80 at the previous step, would be the equation here that we got. So basically the transition in the normal Markov decision process. And again, this satisfies the Markov chain property, because again, here this transition probability doesn't really depend on the t-1 step. So it's a valid Markov chain. And from here in future, we'll be seeing a lot of this, so that states and actions are grouped in pairs and often looked at like one point. So we'll be working with a state action product space quite a lot. So we've been talking about the having need to have some time horizon, basically to look, kind of see in the future for some time. And here, let's first consider the finite horizon case. So when basically the time is limited to some number of integer steps. So again, since this is the goal of the reinforcement learning algorithm, to optimize the parameters of the policy so that we increase the expectancy of the average reward within our finite horizon, we can actually rewrite this. And here we use the linearity of the expectancy, since expectation of the sum is the sum of expectations. And we can move the sum here in front. And what we essentially do here is the marginalization. So basically, imagine that we have each trajectory and the trajectories are distributed according to this probability distribution. And for each trajectory, we essentially sum the rewards at every step. And we can sum this instead in columns. So we can take each possible, each state action pair, and again, they are distributed according to some probability. And then we can, given the probability distribution of the state action pair, we sum the reward for this. So essentially, the first line here is taking the number of trajectories according to the probability distribution and summing the reward for each time step. And this summation would be first in rows and then in columns. And in the second line, we basically do the opposite. So we do the marginalization over the state action pairs. And we, for each state action pair, we sum according to its distribution probability, we sum its reward. And in this formulation, this problem is much easier, because then suddenly we don't talk about the trajectories and the probability distribution of the trajectories, but we mostly talk only about the individual state action pairs. Now, what do we do with the infinite times? So if we have an infinite horizon case, although it's hard to imagine for us as humans, because we rarely have the infinite horizon case because everything is limited in time. But in general, this is a very important property that allows reinforcement learning algorithms to actually optimize the best when they are looking at the infinite horizon case. So first problem is that when a time is infinite, we get this infinite sum, and it's quite hard to work with, although we can still have certain distributions, certain expectations, and we can still find the maximum. it's not convenient to work with. So the question is, if we have the infinite horizon case, do we ever converge to a stationary distribution? Because if we don't have a stationary distribution, then we can't really optimize to anything. And the answer again is that if the transition matrix, or in this case transition tensor, satisfies the ergodicity and aperiodicity, then we do get some stationary distribution. So we always get some stationary distribution given that this T tensor satisfies the regularity conditions. And then this means that usually we will always get some stationary distribution, and given the stationary distribution, we can work with that, because then we can just exclude the T term here and work with that distribution. So basically what we would do is, for convenience, we can divide by T to make this some limited or bounded. And then this will be reduced just to a very simple simple expression where at some point, since at some point the stationary distribution would be the same, we'll be just calculating the expected value of the reward of state action pairs sampled from the stationary distribution. So we start with some different distribution, and eventually in the infinite horizon case, we settle on the stationary distribution, and then we can assess that one. So then let's move to two other very important definitions for reinforcement learning is value functions and value action functions, also known as Q function. So the definition is quite simple. So again, now we don't, we also look at some time horizon with T time steps, and we look at basically at the state at some point T, not state one, but at some certain time T. And then we start with action A at the same time T. So, and then we basically calculate the expectance of getting the reward at basically first apply an action at the time T to state ST, and then following our policy. And then we roll out this for the next T steps and calculate the expected total reward value. And quite similarly, the value function is the same. We do not have any certain action. So here we start with a certain action AT from the first state ST. Here we just go straight with the policy from the very first step. So we just start with state T, and then we follow the policy, get a new action, new state, and then calculate the reward of that. And we sum this reward for a certain time horizon period. Now you can see, since they are almost the same, here the difference is only that for the Q function, we say that we take at the state the time T, we take the action AT, but in the value function, we just say that we don't take certain action AT, we just take whatever action our policy suggests. And then it's obviously some distribution of different actions. So then this value function can be rewritten with the help of Q function. So basically, given the by taking all possible actions given our policy, we calculate the expected value of this of the value of Q function given that action. And if we look at what we are summing here, this is basically what we had before, just with from the state one. So the real objective, as we said, is to actually maximize the expected value of the value function that starts from state one. And state one then would be just drawn on the probability distribution of the very first state. So how to use these Q functions and value functions, and why do we even need them? So basically, as you could see the previous slide, they are quite tightly connected to the goal of reinforcement learning, because they basically represent the total reward that we'll get within the next capital T steps. So there are two big ideas that are used in value-based methods and Q learning. So first idea, let's say we have some policy pi, and it could be anything for now, could be even random. If we know the function, the Q function defined on the state and an action, then we can improve pi. How do we do that? Well, we look at this Q function, since it's defined on the state and an action. We just look at the action that maximizes this value. So it take an action that maximizes the expected reward within the next T steps. And we set our policy to take that action in this state. So we take the probability of taking this action in this state as 1. And you can easily see that this policy is at least as good as pi, and most likely better, because most likely the distribution of the actions according to the policy wasn't 1 and 1 for this and 0 for others. So basically what you do is that you have your policy, you have, assuming that you have this Q function, you look at different actions that you can take. You can see the one that maximizes the Q function, and you take that and say that, okay, let policy be that we always take this action in this state. And by doing this simple thing iteratively, you can actually improve the policy slowly just by using the Q function. And then we'll talk about how to get the Q functions later. The second idea is quite similar, but then it's given rise to a different set of methods. So let's see that we have we do know the value function b at the state s, and we know Q function at the same state s and some different actions. So if for some action a, the Q function given this the current state and this a is larger than the value function of s, then a is better than average, because the value function is essentially the expectation of a Q function given different actions A under the current policy distribution of actions in the state. And if at some of this, for some of these actions, the Q value function is larger than this expectation, so this average, then we should better improve our policy by saying that we should rather take this action because it's better than average. And then you can basically compute the gradients to modify your policy to maybe not set the probability as 1 is the first idea, but maybe just increase the probability according, for example, of how Q function is in this particular action A is better than the value function. And there is a lot built on these ideas in reinforcement learning. So one is basically lies in the foundation of the Q learning methods, and another is lies in policy gradient methods and actor critic methods. So now we have hopefully a little bit more time to talk about the parallel algorithms that exist out there. And there are like few very big classes, and we'll talk in more details about those classes later. So let's here first introduce the general structure of reinforcement learning algorithm. So it's pretty simple. So first we generate the samples, and usually in the reinforcement learning, given that we are in the closed loop, we start with some policy. So some decision-making policy, which could be initialized randomly or by, for example, behavior cloning from demonstration or something. But let's say we start from some random policy. So we generate the samples. And if you remember, those samples are basically the states and the actions. And then we estimate the return or reward that we get from the sequences of states and actions. And apart from estimating, we can also fit a model that basically gives us, for example, the Q function value or value function. And after we did estimate the reward, we use that information to improve the policy. So as according to one of the strategies that we discussed below, for example, or we discussed before. So that would be, for example, doing the gradient, considering the actions that maximize the Q value and so on. And we feed that, then we create a new better policy, use that new policy to generate samples and repeating this. So again, this all is basically expressed in this one equation. The goal of reinforcement learning algorithm is to maximize the total reward within some time horizon. And basically 4 big families of the methods do slightly different things to attain this goal. The policy gradients, they directly perform the gradient ascent on this objective. So basically you have some rewards, you have some parameter theta, and then you just do the gradient ascent on that in order to increase the reward. So this, technically wise, it's probably the simplest method to look at. Then the value-based method is looking at the value function or Q function. And we, for example, represent the Q function or value function as a black box function. And then we approximate it with, for example, a deep neural network. And then we just model that function. And every time we get new samples, we try to look at different actions and select the action that maximizes, for example, the Q function value. And here, so the policy would be just literally just picking argmax of a Q function. Then the actor-critic models, they kind of combine these first two approaches. So they also work with the value function or Q function. But then they take the expressions for those functions and use them to calculate the policy gradient to improve the policy. And finally, we have the model-based methods, which is a huge family of methods where we basically look at the transition states. And since we usually don't know the physics of the world around us, we don't necessarily know the rules of some process, like, for example, a stock market. No one knows the rules of that. And but for example, for the games, you know the rules, so you don't really need to estimate the transition model. You know it originally. So in the model-based methods, you estimate this transition model, so you can also approximate it with, for example, a neural network, and then you can use it for planning. So just like you do in the typical motion planning. So you, for example, try different actions and see which one provides you with the states with a better reward. So you can just kind of model that. Or you can use the approximated model to improve the policy. And there are plenty of different methods how to do that. So here, while we have hopefully a couple more minutes, just on the previous scheme that we have, let's reiterate that policy gradients is we simply evaluate the returns that our policy gives us on the samples that we generated. And then we just calculate the gradient of the estimated reward and update our policy or keep the parameters of the policy to improve it. In the value function-based algorithms, we work with the value functions or Q functions, and we somehow approximate it. For example, fit it to a neural network. So we fit the neural network to the rewards that we get for generated samples, and then we improve it by simply picking up the action that gives us the highest Q value. And the actor-critic algorithm combines two of the above. So we evaluate the returns and we fit the, for example, in neural network to either of these two functions. And then we use that information to calculate the gradient. And in the model-based algorithms, we learn the transition model based on the state of action. And then we could do different things with that in order to improve the policy, or just to create like an ad hoc policy, like selecting an action based on just argmax or something like that. So there are different reasons why we have different algorithms, because it's quite weird that we have different families of algorithms. Why not picking up the best one? And the answer is that all of them have different advantages, disadvantages, pitfalls, and all of them are actually working very well on certain tasks, but neither of them works well on all of the tasks. And the biggest problem here usually includes sample efficiency. So how we sample, do we need to sample at every iteration or not? How does it converge? Because not all of these algorithms have guarantees for convergence. Then some of them work with only discrete or continuous, or better with discrete or better with continuous state spaces. With the infinite horizon or short-term horizons. And it also depends on the functional expressions for different parts of the model. So if it's easier to represent the pi, is it easier to represent the policy, or is it easier to represent the transition model? And for sample efficiency, it's often mostly depends whether it's an off-policy or on-policy algorithm. And basically the off-policy algorithm can improve the policy without needing new samples from the policy, just by improving the results on the set of the samples that we generated originally. And on-policy, for example, in the gradient-based methods, every time the policy is changed, we have a new policy, and it needs to be evaluated on the new samples. And I think we can skip this. So there is a big convergence problem, because in the supervised learning, it's almost always gradient descent, and gradient descent always converges to something, albeit it could be a shallow local minimum. But reinforcement learning is usually not a gradient descent per se. Like in the policy gradient, it is a gradient descent, but it's also often the least efficient and also least sample efficient. And for example, Q learning and model-based, for example, model-based could be so model-based usually involves like a neural network inside, but and that one converges, but the whole algorithm doesn't necessarily converge, because it's only the model estimation, or the prediction of the transition matrix converges, but the whole algorithm doesn't necessarily converge. And there are also like a number of assumptions, such as whether we have a full observability, so whether we can look at the states inside the observation, whether we have infinite time horizons or short time horizons, and the continuity always, or smoothness required, for example, for all gradient-based methods, and so on. So yeah, and I think I got a question, the off policy RL. Yeah, so off policy. Yeah, so here basically on policy is mostly only policy gradients, and actor critic ones can be both on policy and off policy, but in general, here learning algorithms can be off policy, and same is for model based, because for model based we basically try to fit some kind of a model, a transition model, and for that we can just work with the samples that we have, because we already have data, and we just try to fit our function to the data. So basically we don't really update the policy, and there could be no trivial policy, because if the policy would be always the same. For example, we follow some like just try to like enumerate different actions and see the action which gives the best reward, and we estimate the reward based on the transition metrics that we model. Yes. And through this. Yeah, so there are a few examples. Maybe we already over time a little bit, so maybe we'll just glance through them very quickly. So, for example, in the Atari games, that's been solved like almost 10 years ago already now. Basically, you have the full observability, because you know, you basically get the state, so you can easily estimate the state of the system. And also you get the discrete actions. So this one is, I believe, solved with the Q-learning algorithm. And this, because you can have several discrete actions, like going left to right, shoot, and then you can just enumerate those and see which one maximizes the Q function. And these are also cheap to interact, so very cheap to collect data. There are different examples, like again, the games. It's like more complex games, but the situation is pretty much the same. So it's very cheap to collect the data by just playing with yourself. And here you have the discrete states. So again, the Q-learning algorithms work very well. And for example, in robotic applications where you want to dress yourself, or you want to teach robot to run without falling, here you have the partial observability. So it's often that you need, for example, models-based methods to learn the transition, because you don't know the physics, you don't know the rules of the game. So you need to learn that as a part of your reinforcement learning algorithm. But then again, there is plenty of applications where it's expensive to collect data. So for example, the driving, you can't really learn to go off the road too often, because it will be very expensive, and also the collection of data itself is quite expensive. So yes, and I think that the last example that concludes this lecture. So on the next lecture, we'll be looking at value-based methods, policy gradient methods, actor critic, and model-based reinforcement learning, just a little bit more detail to see which one is appropriate where, and so on. So I guess, thank you. Thank you, Chris, for sharing my screen. And do you have any questions?